Professor Cumrun Vafa from Harvard University that will give our colloquium. It will be very difficult to give an exhaustive presentation of Cumrun Vafa work, because he has been one of the leading, I would say, one of the leading theorists in the field for now several decades. He's influenced a whole generation of physicists all over the world. He's been an engine behind the development of the string theory field in theoretical physics. To say all his accomplishments would be impossible for me, also beyond my abilities, but I would say that he's already a lot of ideas that changed this field has his imprint. Just to cite few, mirror symmetry was one his discovery, and his ideas influenced not only theoretical physics but also mathematics. And for example, mirror symmetry opened a whole field of mathematics which didn't exist before, and which is still going on. Then F-theory was, he found a lot of fundamental, important solution of string theories. F-theory is also his name. And the most celebrated calculation, his most celebrated calculation of the black hole Bekenstein-Hawking entropy is also his name on it. This was a fundamental step in the development of string theory, because he showed that string theory is really a consistent theory of quantum gravity. That was the computation that was a landmark, because it showed that there was no doubt anymore. String theory is embodies some fundamental aspect of quantum gravity, and whole sectors of theoretical physics have been opened up by his work. Topological string is one of them, and one has to say that the imaginations and the ideas of Cumrun Vafa has gone through all the field, not only these more mathematical aspects, but very physical one. And in particular, in the last years, so several years, Cumrun Vafa has been opening a new program of research, which goes under different names, swampland, landscape, and that in this very exciting line of research, he's trying to close the bridge between string theory and the experimental evidence. And today, I think we are going to listen to some of his most recent ideas in this field. So this is going to be a great afternoon for all of us, and I think a memorable afternoon for especially for the students, which maybe will remember this lecture for the years to come. So please.
Thank you. Well, I was so moved by such a kind introduction. I don't think I deserve all was said, but anyhow, thank you so much. I'm happy to describe some of the recent understandings we have of how string theory connects to our universe. Let's see if this works. No, it doesn't work. Okay, now the real universe comes in. Okay, thank you. Okay, so quantum field theories have been around for a while, for many, many decades now, and we kind of understand them, as long as you don't include gravity. So without gravity, the quantum field theory is good. They beautifully describe the interaction of all elementary particles using the Feynman diagrams. This is one of them, for example. And so if you ask theorists these days, do we understand quantum field theory? We don't understand everything about them, but we pretty much understand quantum theory. So it's not you're not too much worried about our understanding. So we say we understand quantum field theories. But that's without gravity. So you say, okay, well, what happens if you put in gravity? So including gravity should not be that much of a difficulty, at least naively you would think, because to couple to gravity, what it means is that you take your system and you put it on a dynamical space-time. So instead of having a flat space-time, you think about it like a fluctuating space-time. So in the curved space-time. And what that means in terms of the action is that you first of all introduce the metric, which may not be flat, and you introduce the Einstein-Hilbert term, which is the curvature term, and whatever field that you had before, your matter fields and your gauge fields, you keep it the way it was. You just make the metric general metric, and you integrate in addition over the metric in addition to what you used to do with the action which has this extra term. That's it. So what's the big deal? So you take quantum field theory, you put a metric, you add the action for the Einstein-Hilbert term, you have an interacting system of quantum fields with gravity. Okay, we are good to go. This approach does not work. That's the problem. You take your quantum field theory, you do this, it should work, but it doesn't work. The infinities that appear in Feynman diagrams are incurable, and so a conventional approach to quantizing gravity does not work, as Feynman originally discovered in the 1960s. The most natural conclusion from this would have been gravity cannot be coupled to quantum fields consistently and should always be viewed only as a background. Of course, we know that that's not a good answer, because in our universe we do have both the quantum theory and a dynamical gravity, which is not just a background. So therefore, there's something strange going on. Naive thing says it shouldn't be possible, but we know it is possible because we live in one. So therefore, the question is, how do we solve this problem? So this is one of the biggest problems that was facing already back starting from the 1960s. So string theory offers a solution to this problem by replacing point particles by extended objects, in this case strings, loops of energy. And it leads, surprisingly, to consistent theory of gravity. It is very miraculous how it becomes consistent, but it does. And in this context, the point particles that were part of the word lines that we consider in the context of the Feynman diagrams in the quantum field theory setup gets replaced by these fattened picture where the lines, the word lines, are replaced by these tubes or word sheets, because the strings are now moving. They are two-dimensional. They span a two-dimensional space-time, part of the space-time, and they interact by splitting and joining more or less the same way that particles do, but now in a way which is less singular than Feynman diagrams. So the diagrams here are much smoother than the particle things, because the particle diagrams have these singularities where the particles emit and absorb in a singular fashion in space-time. In string theory, they're kind of spread out. The point of interaction are spread out in regions, which is precisely the reason that the theory is nicer than particle theory in the context of gravity. So these resolve the problems that Feynman had with quantum gravity. Is resolved precisely because of the fact that the interactions are kind of smeared over the length scale of the string. But this raises the question, can we get every consistent quantum field theory in 4 dimensions coupled to gravity from string theory? String theory comes with 6 extra dimensions. We have 3 plus 1 space-time dimensions that we are familiar with, but string theory is not consistent unless you add 6 extra dimensions, 6 spatial dimensions. And so to avoid contradiction with experiments, we have to assume that these 6 extra dimensions are tiny spaces, compact spaces like sphere or circles or much more complicated objects that one can in principle imagine. Otherwise, you would be in contradiction with the fact that we only see 3 dimensions in the macroscopic world. And so this raises the question about what the solutions of the extra dimension are, and there are many solutions that arise, and I'm here drawing a cartoon. These are not realistic pictures, but the cartoon of complicated geometries that people consider. Interesting manifolds come in that solve the Einstein's equation in 6 dimensions, Many of them are related to manifolds called COLLOQUIUM manifolds and other things. So there's a whole industry of constructing nice solutions to string theory by choosing these compact six-dimensional extra space. So you think about the macroscopic space as like these yellow directions. So these are, you can think about the yellow directions as the three spatial directions. And at each point in space, you should imagine having a tiny extra dimension, which is kind of invisible to the 3 dimension you have, so there are extras. And in principle, there could have been different shapes, but typically in a given region, you expect it the shapes to be the same, not depending on which point you're at. So here I'm describing an example of what this extra dimension looks like. This is, I'm taking a simple example of this purple picture I'm putting here is like torus, a 2-dimensional torus, like a donut. And the macroscopic 3 dimensions I'm representing by this blue sheet. This is the bigger dimension. And you can have excitations of strings, which could be, for example, wrapping of the strings around these cycles of this geometry in different forms and different fashions. At a given point in space, you take a string at the given point in space, you wrap it around the corresponding torus, which is on top of that point, in different ways. And each one of them give you different particle as you see it from the 3-dimensional perspective. So you get different kind of particles depending on which kind of excitation of the string you consider. So the spectrum of what you see in 3 dimensions will depend on the details of the geometry of what this extra 6-dimensional space is. So the physics that we experience in terms of macroscopic objects in 3 dimensions will be different depending on which extra dimension and how the geometry of this extra dimension looks like. So one particular geometry, one particular 6-dimensional space could, for example, give rise to a theory in 4 dimensions with a gauge group SU4 with 2 generations of matter, for example. Another one might give you a different group with a different representation of matter. And this raises a question. Suppose I didn't care about how the geometry looks like. I just wanted to know whether you can get any consistent quantum field theory. You just say, I don't want any specific one. I want, let's say, SU3 cross SU2 cross U1 with 3 generations. Or I want SU100 with 10,000 generations. Can you give me everything I want by choosing some space? If that was possible, then you could kind of forget about the left-hand side and just start with the right-hand side. Who cares about the left-hand side? What do you learn from that? Surprise is that it seems we cannot get arbitrary quantum field theories by choosing these 6 extra dimensions in a different way. Indeed, we seem to be only getting a finite number of quantum field theories, a finite number of them that are possibly arise in the context of string theory. For example, suppose you ask the theory in 4 dimensions, which has the maximum amount of a symmetry, which is supersymmetry. In this case, you can ask, okay, what does this theory look like? The theory in 4 dimensions with maximum amount of supersymmetry is fixed completely by choosing a gauge group. You choose a gauge group, and that completely fixes it because of the huge amount of supersymmetry. So that's a very simple example to consider. And in fact, these theories are among the best theories in quantum field theory because the theory is finite. It's beautiful. In terms of quantum field theory, the divergences disappear, and it's nice for every gauge group. For every gauge group, you get a beautiful theory in 4 dimensions, which is in fact scale invariant, in fact conformal invariant. It's a very nice theory. You try to couple this to gravity. It depends on a gauge group G, and you try to say, okay, is it okay if I couple this to gravity? And the answer is no, if the rank of the gauge group is big. For example, if you take the gauge group to be SUM, and if M is bigger than 23, the theory is inconsistent with gravity. So out of the infinitely many possible examples of arbitrary ranked gauge groups, only a finite number are consistent. Even though the quantum field theory itself was perfectly good, there is nothing wrong with that quantum field theory. But when you want to say if you can get it in the low energy regime from a quantum theory of gravity, then not everything is possible. And suddenly, the infinite set gets truncated to a finite number of possibilities. And this example beautifully illustrates that gravity changes the perspective that we have from quantum field theory. So the question is why? Why did it happen? What is this perspective that tells you that infinitely many possibilities are suddenly truncated to just a finite number of them? It's as if the finite number of things that can arise is like kind of a jewels that gravity allows, and the rest of them are kind of not good. So it's a very, very specific sets that are allowed. So this says, therefore, we learned the lesson that if you take a generic consistent quantum field theory, it cannot be consistently coupled to gravity. So Feynman was, after all, right. A generic quantum field theory is inconsistent with gravity. Only a finite number of jewels exist which can barely be consistent. And these are the ones we are getting in string theory. So that's the way, with the perspective we have to take into mind, that we are having a very limited subset of possibilities that are kind of arise. So this raises two questions. Does the fact that most quantum field theories do not arise in string theory a deficiency of string theory, or a general conclusion about consistency requirements for quantum gravity? One could have said, you know, it's a problem of string theory, not the quantum field theory in general. String theory just cannot get them. That's a problem for string theory. That could be one attitude. Or could it be, no, it's really about consistency of quantum gravity, and string theory just is an illustration of what the problem is. Evidence is emerging that this is not a deficiency of string theory. But there are subtle reasons for consistency of quantum gravity which demands these. And connection with basic facts of quantum gravity, such as unitarity and quantum consistency of black holes, which does not rely on string theory, leads us to similar conclusions. So therefore, the ideas which are beyond string theory, which is just the things that we believe any quantum theory of gravity should have, like consistent story about what black hole evaporation looks like, in particular its unitarity and all those properties, already give you results which reinforce the ideas that we get from string theory. So we believe, therefore, the lessons that string theory is teaching us is a universal lesson, not just about string theory, but about any potential consistent theory of quantum gravity, even if there is one beyond string theory. So the second question this raises is, what criteria distinguish a good quantum field theory? A good quantum field theory, by that I mean a good one which can couple to gravity or arise in the low energy limit of gravity, what we call, by definition, part of the string landscape, from the bad ones, which we call belonging to the part of the swampland. The bad ones means they cannot be coupled to gravity. The swampland program is to understand what these conditions are. Now, you might say, why are we being negative by trying to rule out theories instead of saying what is allowed? The problem is that what is allowed is measure zero. The set of possibilities, as I told you, are finite in an infinite set of possibilities. And therefore, it's much easier to say what is not possible than to say exactly which one appears. So therefore, it's an easier, more manageable program to rule out what cannot appear than the other way around, to say what is allowed. So the swampland program, of course, is the complement of the landscape construction. Namely, you say, if it's not allowed, then you know where to look for the ones at least that can be possibly there. So this is how we think about it. The space of landscape of possibilities are of a vast one. And depending on what kind of solutions you put in, you get only a specific small subset of what allowed possibilities are. So this green space is the set of all possible consistent quantum field theories that could have existed. But almost all of them belong to what we call the swampland, that they are not consistent. And only a few of them are possible, which we say they belong to the landscape. And of course, one of them is our universe among the possibilities. This already tells you that the naturalness ideas that appear are going to be very different if you do not include quantum gravity. If you ask a general quantum field theory, what is a natural quantum system, you get one conclusion, because you're talking about the full green space here. But if you're asking, no, if you assume gravity is also part of the game, then the prior changes of what is consistent, and then you get a different notion of naturalness. What is possible within that subset, within that prior, is different. And therefore, then this gives rise to a new notion of naturalness that is missing in the quantum field theory currently. So my aim of this talk is not to try to give you everything we know about something. That's not going to be possible. However, what I'm going to try to do is to give you a flavor of some of the things that we have discovered in the context of what are some of these criteria which distinguish good from bad theories. So what are these swampland criteria? I'm just going to give you some prominent examples of them. And so basically 7 possible examples, categories I'm going to discuss here today. First one is that a consistent theory coupled to gravity cannot have global symmetries. That means that if you have a symmetry in your theory, in your quantum theory, it better be a gauge symmetry, like the one we are familiar in the context of the usual electromagnetism. You have a conservation of charge, but that's related to the electric force, the magnetic force. So that is an example of what I mean by the theory. So if you had a theory for which you have so if you have some charge conservation like electron number, then it better be that also has electrical field associated with it. That's not clear why it had to be the case, but quantum gravity demands that, as I will mention. Why? Second thing is related to uniqueness of quantum gravity. As I told you, there could be various kinds of consistent solutions to quantum gravity with different quantum field theory systems. And naively you say, what's the relation between them? I will explain that the extension of the first criteria, the no global symmetries, demands that these other theories are all related to one theory. The theory of quantum gravity has to be unique, and this is related to the lack of global symmetries. So the uniqueness here is quite interestingly connected to no global symmetries. The other one is that all charges, since I said there are no global symmetries, that means every symmetry is gauge symmetry. And the next criteria is that all the gauge charges appear in the spectrum. So if you have a gauge symmetry, then you should get all the charges. So for example, you cannot have a Maxwell theory, electric and magnetic field, with no charged particle or no magnetic charged particle. You cannot have, for example, only electric charged particle and no magnetic charges either. Every charge that's allowed is there. It's forced. It's not just luxury. You have to have it. Quantum gravity says you cannot avoid all the charged states. That's called the completeness hypothesis. In the quantum field theory, the range space for the fields could be infinite. There's no problem. You can take any field and have an arbitrary range. For example, you take a scalar field, you take a field to go from minus infinity to plus infinity. There is no problem. In quantum gravity, not so. The range of effective field theory, if you want to keep the same effective action, is finite. And this is called the duality conjecture. It's related to dualities. If you go too far in field space, a dual description takes over, and you have a new description. And what your effective field theory breaks down, and new degrees of freedom have to be included. You don't have the luxury of just going all the way to infinity without including them. And if you include them, there's so many fields you have to include that your original theory breaks down. The theory of quantum theory of gravity must admit light higher dimensional objects. You cannot just have point particles. You need higher dimensional objects like strings. Gravity, in any theory of quantum gravity, is always the weakest force. In our universe, gravity is the weakest force. But this tells you it's not just in our universe. Any consistent theory with gravity must necessarily have gravity as the weakest force. This is called the weak gravity conjecture. And finally, I want to describe the restrictions on having critical points with positive value of potential. And this is relevant for our universe because our universe, we have a dark energy which is positive, corresponds to positive potential. So there are severe restrictions, it turns out, in trying to get this situation with having minima or metastable minima in the context of string theory. And I'm going to talk about that. These are related to what's called the de Sitter conjectures. So these are the 7 items I'm going to talk about today. But before I do that, I want to say that I want to tell you some basic facts about black holes, because black holes run the show. Fixed charge Q and a mass m for the black hole. As long as the mass of the black hole in Planck units is bigger than the charge, there is solution to Einstein's equation. So we can write the macroscopic big black hole with big mass as long as the mass is bigger than the charge. The extreme case when it's just equal to charge, the limiting lower limit of this, can also occur, and these are called the extremal charged black holes. Black holes have thermodynamic properties. This was discovered by Bekenstein and Hawking by studying semi-classical theory of gravity in the presence of black holes. And what that means is that the black hole should be made of as more entities, some microscopic entities, which give you an entropy of number of degrees of freedom. Even though the number of degrees of freedom of the black hole naively, classically is 0 because there's a unique solution in Einstein theory, the semi-classical treatment of Bekenstein and Hawking shows that there must be many more degrees of freedom, and in fact, the number of degrees of freedom of the black hole, the entropy of it, is 1/4 the area of the black hole in Planck units. Area of the black hole, I mean the area of the horizon of the black hole. The horizon of the black hole is, of course, the point of no return, that no light can emit from inside that region. So the area of the event horizon of the black hole divided by 4, measured in Planck units, is the measure of the number of degrees of freedom of a black hole. So these facts I'm going to use in the discussion today. Now I want to describe why there are no global symmetries in a quantum theory of gravity using black holes. The idea is relatively simple, because suppose you have a charged Q which does not have any electrical field. It's conserved. You just count how many charges you have, but no electrical field comes out of it. You consider a big black hole and throw the charge, which is conserved, inside the black hole. So the charge is gone. The charge is inside the black hole. You throw it in. And I will now try to explain that they would not be conserved. Why is that? Well, you throw the charge inside, but there is no electrical field coming out, because I'm assuming that these are global symmetries. There's no gate charges. So therefore, no electrical field comes out. So from outside the black hole, you cannot detect the charge. There's no electrical field, force line coming out. Therefore, when they and the black holes evaporate because of its thermodynamic properties, as I mentioned to you before, and as they are evaporating, they don't prefer the charge positive and negative charges when they emit thermally, because there's no electrical field or anything which prefers one versus the other, and therefore they emit plus and minus charges Q equally. And so as it evaporates, you get rid of all these charges in equal amount, and by the time the black hole evaporates, you get nothing left, where you have only emitted equal number of positive and negative of these quantities. And so you started with one charge originally, and then you put it in, and now you have none. So you violate the charge conservation. So you cannot have global symmetries in a quantum theory of gravity. And black hole is is a way to see it, because you can have a virtual black hole, which kind of gives you a process where these get disappeared. So there is no symmetry, global symmetry in quantum theory of gravity. You see, black hole plays that role because of this, the evaporation of the black hole. Uniqueness of quantum gravity. A generalization of the no global symmetry conjecture, the fact that there are no global symmetries, implies that any consistent theory of gravity can be deformed to any other one through finite action. So I told you that there are many possible solutions depending on what you choose as the internal geometry of string theory. I said one might give you a gauge group SU4, one of them give you SU100, and whatever, different ones. But the main point is that any one of them used, it doesn't matter. You can create any other one by a finite action process to go from one to the other. So if you start with any given, for example, compactification, you can go to any other one with a finite process. The fact that you can go from one to the other is is characterized mathematically by what's called the cobordism class. You can see what manifolds can go to what other manifolds with a non-singular intermediate extra dimension, one higher dimension, so that these appear as a boundary of them. And the statement is that in general, one might naively thought that there are different classes, that some cannot go to the other ones, that there could be selection rules. But if there are selection rules, then that means there are symmetries which distinguish them. But I just told you there is no symmetries in the quantum theory of gravity. So having no symmetries means there is no criteria to distinguish them. That means everyone could go to any other one. The quantum theory of gravity is unique. So uniqueness of quantum gravity is deeply related to the fact that there are no global symmetries. And that's deeply related to the black hole. So this is connecting these facts together in a nice, simple way. The next criteria is that all the charges that appear in a gauge theory, so every symmetry is gauged, and the question is, can all the charges appear? The next criteria says all charges that can appear will appear. Without gravity a priori, no reason, for example, as I just told you, a U1 Maxwell theory, you don't need to have any charge state. In principle, you could have E and B fields with no electric or magnetic charge at all. But now I will explain why this is not possible in the quantum theory of gravity. Consider a black hole of mass m and charge q. As I told you, if the mass is bigger than its charge, there is such a black hole. Moreover, as I said, the number of such states, according to Hawking's and Bekenstein's formula, is given by the exponential of the area over 4. That's related to the fact that entropy is 1/4 of the area. Well, this already tells you that, therefore, there is a state in your theory with that mass and that charge. That's what entropy means. Not only one, but many such states, given by this number. Take any one of them. Now, take the case where the q is replaced by q plus 1. Again, there will be many of them, but for the same reason of Bekenstein-Hawking. And take one of them with charge q plus 1 and the other one with charge minus q and collide them. Well, then by charge conservation, you get one with charge plus 1, and that is an allowed state. And therefore, you learn that charge 1 appears in your theory, and therefore any charge appears in your theory because you can now collect any number of them put together. So therefore, the existence of black holes with a given mass and a charge, which is dictated by Einstein's theory of gravity, and using semi-classical statements of Bekenstein and Hawking, you already deduce that all charges should appear. Now, this already means that magnetic monopoles must exist in our universe, regardless of grand unification. People sometimes use the idea that, oh, if you have grand unified theories, you will get magnetic monopoles. This is telling you, regardless of unification, there must be magnetic monopoles, because you can consider black holes with magnetic charge, and they exist too, and therefore there must exist, for the same reason, magnetic monopoles. So this is quite powerful, because it tells you that some basic facts about our universe are forced on us because of gravity, even though it sounds like it should be a quantum field theory statement. So indeed, a quantum field theory, if you did not include the gravity, may or may not have had a monopole state. Not so if you have gravity in the mix. Gravity says there better be, all the states are there. So it's quite restrictive. The next one is finite range for fields. This is related to duality conjecture or distance conjecture. Consider a field phi, a scalar field. Without gravity, we have no restriction on its range. For example, it could go from -infinity to +infinity. However, with gravity, it seems the range of the fields for a given effective theory, if you fix your effective description with the number of particles and forces and all that fixed, cannot be any bigger than the Planck scale. So the range of the field is order 1 in Planck units. You cannot go too far in the range. And what happens in the field space is that scalar fields come with some kinetic term in the action with some two-point function which corresponds to a metric as a function of phi. So this kinetic term defines the notion of a metric on the field space using Gij. And you can use that metric to measure distances in the field space. So measuring these distances gives you a geometry to these values of the scalar field. Then you can say what happens if you go to far distances in field space. Suppose you take one point in the Earth space and go to farther and farther points. What happens? It turns out that when you go to farther and farther distances, you get a new description happening, because what happens is that as you go to far enough distances, you get a tower of states coming down with masses going like e to the minus alpha phi. So as phi goes to large values, you get the exponentially light tower of states emerging. Not just one, an infinite number of states becoming light. So your effective description breaks down. You cannot say, I will include one more particle or two more particles. You have to include infinitely many more particles, which means your description breaks down. You need a new description. This is the dual description that takes over. So the fact that in string theory we have discovered duality symmetries is precisely the statement. That is, when you go to different regimes of parameters, new descriptions emerge that were not supposed to, that were not expected. And this is deeply related to what's called this distance conjecture or duality conjecture. Infinite distance in field space demands a new description. The old description breaks down. A potential application of the distance conjecture is to the cosmological constant in our universe. Cosmological constant in our universe is an extremely small parameter, 10 to the minus 122 in the fundamental units. It's very small. In the fundamental units, you should think about the cosmological constant like exponential of a field, and therefore it corresponds to a very large number in the Planck units for the field. And therefore, this means that there should be a tower of light states, which m goes like lambda to the some power of a, for the same reason I just telling you. This is for our universe. You should expect a light tower of states. What is this light tower and what is this? A. Indeed, it can be argued using some other observational input, not just theoretical, but observational input, that in our universe the value of A is about a quarter, and that the light tower is graviton excitations in an extra fifth dimension of a scale of micron. So this would be a natural prediction based on just the simple idea of the distance conjecture applied to other observations we already have as inputs to this prediction. So this is quite a remarkable prediction, that we will be predicting an extra dimension of the scale of a micron as what we could call the dark dimension. The next criteria is that the theory of quantum gravity, any theory of it, should have extended objects. There must be extended objects, like in different corners of the quantum gravity might look different. For example, in the M theory, we have membranes as extended objects, two-dimensional. In string theory corner, you have one-dimensional extended objects. There is no corner which is zero-dimensional objects. Always you need higher dimensional objects to arise. In fact, we can kind of try to understand it as it's related to this distance conjecture, the distance conjecture I just told you about. Suppose you start with the theory of gravity and put it on a circle, and then you get one lower dimensional theory. The radius of the circle can be viewed as an extra field because it's a theory of gravity, so the radius is dynamical. And if you put it in, you find that the Lagrangian you get is 1/2 grad phi squared, where r is given by e to the phi. So the degree of freedom describing this extra radius is a scalar field, size of it. You can take the large limit of r by going to the large limit of phi. I told you that when you go to the extreme limit, large phi, you must get light states. Large radius, what do you think is a light state? Well, these are in fact the graviton excitations, which if you have a large wavelength, their energy is low because they go like the inverse of wavelength, and therefore these are what we call the KK modes, Kaluza-Klein modes, which are becoming light because of the wavelength is becoming large. So that's in other words, the energy for these modes goes like 1/r, which is e to the minus phi, and therefore they are light. So that's the tower I was talking about, are the harmonics of these extra waves on this extra of this extra big circle. However, we can also go to the other limit where phi is very, very negative. In other words, when the radius is very, very small. Again, that's an infinite distance limit, and we expect some light tower of states to come in. But field theory, if it was a theory, if the quantum gravity was the theory of point particles, tells you there is no light particle. In fact, if you go to the limit where the radius goes smaller and smaller, the theory gets simpler and simpler because the excitations of momentum around the circle become infinitely heavy. So you throw them out. So the theory truncates to a much simpler theory where you just ignore the extra dimension as a coordinate. So it's what we call the dimensional reduction of the theory. So the theory just gets simple, and there's no light tower. But that's wrong. I told you that when you go to the infinite limits, you should get, the effective description should break down. You should get a light tower. But the theory of point particles will not give you that. So to get that, you need an extended object in such a way that when you have this extra dimension, you can wrap around it, and they become light in the limit that the extra radius becomes small. Like in string theory, you can strap a string around this extra dimension. When they become small, they become light tower that I was talking about. Or if you have a membrane, like in M theory, you wrap one of the legs of the membrane around the circle, and then again, they become light. So this is the two ways you can happen. And so the only natural mechanism, therefore, is that the quantum theory of gravity must have extended objects with higher dimensions, like a string or a membrane or something like that. Gravity is the weakest force in our universe, and in any theory of gravity, the claim is. Why? In examples in string compactification, we have seen that this is always true, of course, that gravity is always the weakest force. So, for example, in 4 dimensions, when you talk about the gravitational force, if you have two charged particles, the electric repulsion between them goes like the square of the electrical field over r squared, the usual Coulomb repulsion. And the gravitational attraction is m squared over r squared. And in our universe, the fundamental entities like electron have a mass in Planck units. Here I'm writing the mass in Planck units, so that's why there's no Newton's constant in that formula. So the mass in Planck units is smaller than the electrical charge. That means that the gravitational attraction between two electrons is much weaker than the Coulomb repulsion between them. They always repel more than they attract by gravity force. That's in our universe. But it's also true in any conceivable universe. In any example of string theory, it's true, and now I will argue to you that's true in any conceivable consistent theory of quantum gravity. In our universe, this mass is about 10 to the minus 23 in Planck units compared to E, which is 10 to the minus 1. And therefore, in our universe, it's well satisfied. This is certainly true, but it's true in every possible universe, as I will try to argue. And the argument is, again, black holes. Black holes play the role all the time in all these arguments. It's one of those central objects which distinguishes quantum theory with and without gravity. So you consider, as I told you, when you talk about charged black holes, you can have a limit where the mass and the charge are equal. The mass is typically bigger than its charge. The mass of the black hole is bigger than the charge, but there's an extreme limit where it's just equal, the extreme of black hole. And now what we're going to do, consider the black hole of charge Q, and consider emitting a particle of charge small q and small m. The fact that black holes evaporate and disappear must allow for this to be possible. So you should be able to emit charged particles, small charge q and mass m. So in other words, you go from q and m to q minus q because the charge emitting, and your mass goes down by m minus m. However, what you're left with is a black hole which should satisfy the condition for it to be a black hole. But I told you that the mass of the black hole is always bigger than its charge. So for that to happen, you learn that the mass, the new mass, which is m minus small m, should be bigger than the q minus the small q. But you started with m equals to q, and therefore you learn that small m should be less than the small q. So the thing that you're emitting should have a mass less than its charge. That's exactly what we were saying for the electron. electron's mass is less than its charge. That will explain why the gravity is the weakest force. So again, the condition that is evaporation of black holes, extreme black holes, the consistency of that demands that the weak gravity conjecture is true. There is further evidence for the weak gravity conjecture. So consider pure Maxwell theory coupled to Einstein's gravity. So as I told you, they cannot be just the pure Maxwell's theory because of the swampland criteria. But let's imagine, as an action, you can write down just gravity plus just electromagnetism as fields with no extra matter. Let's just imagine that. It actually has been found that this kind of system can lead to naked singularities. That if you consider regions with strong electrical field, you find regions where they're singular, but which are not cloaked with a horizon, so they can see them from infinity. So it's not hidden inside the horizon. So this violates one of the principles that Penrose suggested about the censorship of these singularities by having some kind of a horizon around them. But this gives you a counterexample, namely a Maxwell theory coupled to gravity can give you a counterexample for this. However, I'm claiming this cannot be consistent with quantum gravity for two reasons. One, I just told you that the spectrum should be complete. So if you have Maxwell theory, you better have charged particles. Okay? If you put charged particles, then if you go to the regime of strong electrical fields, and if you have light enough charged particles, you pair produce them from vacuum. If the electrical field is strong compared to their mass, then you will create them. But indeed, the weak gravity conjecture says that there are light charged particles. The mass is less than its charge. Therefore, the electrical field could potentially produce them. And it exactly happens that precisely when the electrical field is strong enough to create the singularity, it's also exactly strong enough to pair produce. Just about the right scale. So exactly, the weak gravity conjecture comes and rescues this censorship. So this property, which has nothing to do with any abstract aspect, it just has to do with the singularities being hidden, is amazingly consistent with these features of swampland program without being put from string theory. So I'm trying to emphasize here not using string theory and just using general arguments of physics like this one. Of course, in all the examples in string theory, we know the weak gravity conjecture, of course, is true. So this is how we came up with these kind of ideas, but now we have a better understanding of why they are there. There's another application of the weak gravity conjecture to our universe. We live in a space which has dark energy, positive energy, and it's approximately constant, or maybe exactly constant. And this is what we call in our universe, what it could be called the de Sitter phase, the phase in which we are in the accelerated expansion of the universe has taken over. And this is the de Sitter or the quasi-de Sitter phase we are in. In such a case, you can still consider the evaporation of the black holes in the same way I told you, but now you can consider large charged black holes, and their evaporation gives you the opposite direction for the inequality I was telling you about. I won't give you the details, but you find that the mass is not only less than the charge, but actually is bigger than the value of the dark energy to the 1/4 times square root of Q. So you get the mass which is bounded by the lower and upper regimes now. So you learn, in the context of the electron, that the mass of the electron is bounded by 10 to the minus 1 and 10 to the minus 31 in Planck units. It's 10 to the minus 23 in our universe. But this already tells you that even though we could not say exactly what the mass of the electron is, we can make a prediction which is borne out by this regime. Of course, this is not a strong prediction because the range is so wide, but still, it tells you that there's a prediction here. That even though it's a bit not precise, but it's it gives you a big range, but still it demands some restrictions. The lower bound is close to the bound that we see in the neutrino mass. By the way, something about this is interesting. Here, we could have reversed this reasoning. Namely, if you start with the mass of the electron, which we did know before the measurement of the dark energy, we could have predicted that some bound on the dark energy, because the dark energy has a particular relation. And you learned that the dark energy in fundamental units should be less than 10 to the minus 88 or something like that. It's of course about 10 to the minus 122, so it's much smaller. But already saying that it's not order 1 and it's much, much smaller just because there is an electron is already a strong statement. So we could have predicted that the dark energy cannot be too big in some sense from this kind of picture without any observations. So the final topic I want to talk about is restrictions on critical points with positive values of the potential. So as I said, we live in a universe which has positive dark energy. This is an important question for early cosmology. For example, in the context of inflation, we typically need a potential which has some flat regions with positive value, and there's some lower regions which is sit stable, maybe a metastable kind of a point, with some value of the potential which you can identify potentially with the dark energy. Could you have such a situation? For example, that's a question. Inflation would suggest yes, you would want to have such a situation. You want to have a relatively long region here, and a flat and long region with positive value of V, and then dropping down to some minimum like this. Is this possible, or there's a problem or not with this? This turns out to be among difficult problems to investigate in string theory. We don't have good techniques, unfortunately, to assess these problems, precisely because positive energy demands breaking supersymmetry. We cannot have positive energy without breaking supersymmetry. And when we break supersymmetry, it turns out many of the technical tools we have in string theory, we lose the power to compute things in a way that we can trust. So we don't have too many tools to assess this precisely. So we are on a limb trying to make predictions. But I will try to tell you what we know about this very important but difficult problem. I told you that if you take a field space, there's a distance on the field space coming from the kinetic term for the field space. And you can go to large distances in field space. These are these regions that I was telling you about. It turns out in these regions, whenever you find a non-zero value of V, it's always exponentially goes down. It always goes to zero exponentially fast. You cannot have something, for example, which goes to a constant at infinity. So that's already remarkable. So you have to have it fall off exponentially down. This we are sure about. This we can prove in string theory, that at far enough distance in field space, not arbitrary potential appears. In fact, it should exponentially go down. That's a requirement. So you have potential which goes like e to the minus some constant times phi. Moreover, you can try to find the exponent here by considering V prime over V, and you find that there are bounds that you get from string theory example. In string construction, you get bounds like V prime over V of order, I'm using Planck units here, V prime over V is of order square root of 2/3, for example, or always above that. So you have the slope which cannot be too flat. It's always falls fast enough. So therefore, the next question is, okay, what is our universe? Our universe, we have dark energy. One possible way would be something like this, where your potential comes up and then goes down and then goes up like this, with some minimum there somewhere. This would be called a de Sitter space. If we have a de Sitter space, that point over there is going to be metastable at best, or unstable, in the sense that that point over here is above 0. And I just told you at infinite field space, you go to 0. So any conceivable realization of positive energy in the universe that we are living in will be unstable ultimately, or metastable at best. So our universe will decay. That's, I think, one of the conclusions we don't have any doubts about in string theory. So this is a consensus within string theory that the dark energy is going to be basically seals the fate of our universe. We are going to decay. The question would be exactly what form and how fast is what's still being debated, but not the fact that it will decay. So a condition for swampland, the de Sitter swampland constraint, suggests that perhaps that this feature, that V prime is bigger than V, maybe applies also inside. But we don't know, because the inside regions, the coupling constants that we are dealing with are order 1 and strongly coupling limits. So we have less technical abilities to study those. So we don't have a sure techniques to assess the statement in those regimes. But it's quite remarkable that not arbitrary potentials appear, and so we have very strong bounds of how you can get these potentials to suggest that there could be something like, so one version of this conjecture suggests that you can have either too much a slope, or you get an unstable, which has too strong instability. And another version, which is what's called the Transplanckian censorship conjecture, suggests that if you take if you have an expanding universe, and if you have subplanckian modes, Planck modes which are smaller than the Planck scale, when the universe expands, these modes get out of the Planck scale, and then sometimes they can be so big that they cross the horizon of your region, and then they freeze out. And if this happens, you have basically converted a Planck's length object to a physical macroscopic scale, which is frozen. And this conjecture says this can never happen. This is Transplanckian censorship conjecture. This conjecture gives you a bound for the slope, which seems to be satisfied at large distances. So it kind of gives you a rationale for why is it that the potential seems to fall off at infinity. If you take this description, you get a bound for the age of the universe, which is given by the Hubble length scale and so on. So swampland conjectures and inflation kind of don't go together very well. So in fact, many of these ideas in swampland kind of make inflation very hard to happen, if at all. And one cannot rule out all possible inflationary models. For example, you can have some exotic parts of many field inflation and this and that cannot be necessarily ruled out. But the most garden variety, the simplest form of the inflation, seems to be incompatible with this inflation in swampland ideas. So this suggests that there must be different ways to realize the very early universe. And there are some restrictions coming also from the TCC and so forth, which tells you that even if inflation is satisfied, the regimes of parameter are so restrictive and so fine-tuned that's hard to believe that they are realistic. So for example, the R parameter, which is this mode that people are looking for the tensor modes in the gravity, would be extremely small, if at all possibly realized, if they are to be consistent with these criteria. So one might wonder, why is it that if we are saying that there's an issue with inflation with the swampland, then what is going on in the early universe? What replaces that? You see, inflation came from a period of thinking in theoretical physics where you want to have a simple model which describes everything. One model describes the early universe, late universe, everything. You just add one field or a few fields, and you just have a potential, very simple. And you get a lot of the problems solved by this simple model. So what's the problem? That's the natural worry about this. Well, one problem is that not everything goes in the context of quantum gravity. You cannot just say, I want this, what's the problem? I gave you many examples already that naively seemed okay with quantum field theories, but they just don't appear with quantum gravity. So just thinking that you can write the model Lagrangian, then what's the problem, is not a good answer. But there's actually something more philosophical, that we expect something else to happen. You see, early universe, if you go back in time, the temperature should get larger and larger. So imagine going backwards in time. The temperature is going up, 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 up as we approach the Big Bang time. Oops. This is certainly not mine. If Trump doesn't like this, okay. Okay, I'm good. Okay. Okay, so something philosophically goes very bad, which is the following. If you go to very early universe, going backwards in time, temperature goes up, up, up. This is extreme regime. Extreme regime means the following. If the temperature is going up, you can think about temperature in terms of the Euclidean thermal radius, which is inversely related to temperature. So temperature going up means radius going down, going towards 0. But I just told you that as the radius goes to 0, you should get light degrees of freedom. So you should get new degrees of freedom. Effective theory you're dealing with should break down. You should get new degrees of freedom. You should get a dual description. So the description that we are having from string theory tells you that you should not expect a single theory describing the large temperature and the small temperature. There must be a new description at high temperature. And that's where our universe emerged from. So we must have undergone a duality transition. We must have undergone a period where the dual description was happening, and then we came to our matter. So what in inflation model they talk about reheating is the emergence of the dual description, which is our universe. That's the way this model would work. And there are simple models which suggest how that may come about. Oops, what happened here? Yes. So again, you can use some of these swampland conditions to get some bounds on the lifetime of the universe. If you take, for example, the Transplanckian censorship conjecture, that sub-Planckian modes cannot exit the horizon, you get the lifetime bounds for the potential age of the universe, potential lifetime of the universe, to be of the order of 1 over the square root of the dark energy, log of it, which is about 2 trillion years. So there are some interesting bounds that emerge from these kind of scenarios. Either of the de Sitter conjectures explain the why now problem. What is the why now problem? The why now problem is, just recently in the cosmological epoch, the dark energy has taken over. Why do we happen to live in such an interesting time? Why didn't we appear much, much later? Why do we live just at the time where the dark energy has taken over? Well, one explanation will be offered by the de Sitter conjecture, is that the answer is because the lifetime of de Sitter cannot be much larger than the Hubble scale, the scale of the universe that we are in. So therefore, whenever you are in a universe which you measure the dark energy, you are basically measuring the doomsday of that universe. And so therefore, the fact that we live in such an epoch is the only time we could have lived. There is no much longer time. So this would explain the why now problem. So the de Sitter conjecture, the why now problem, is an evidence for the de Sitter conjecture. These ideas can also explain the coincidence problem. What is the coincidence problem? The cosmological coincidence problem is, so at the early universe, the dark energy was dominant. The radiation mode was dominant. So the universe was expanding in what we call the radiation phase. The matter density was much less than the density in the radiation. Then the radiation energy density drops down and the matter takes over. But it turns out as the matter takes over, almost right then or slightly thereafter, the dark energy takes over. So in other words, the matter and radiation density equal almost exactly when the dark energy is equal. So that's called the coincidence problem. Why do these three energy densities agree at one particular time? Why do they coincide? This is called the cosmological coincidence problem. And it turns out that this can be explained. The excitations of the graviton, I told you that there's the existence of this dark energy suggests the fifth dimension. And this suggests that the composition of dark matter in the universe can be naturally related to the extra excitations of these harmonics of the graviton. These KK modes are just higher modes of the graviton in this extra dimension. And if you just put that into the model, you find that this automatically leads to the idea that the matter and the radiation have equal density precisely at the scale of the temperature that the dark energy is about to take over. So this explains the coincidence problem as well. So let me conclude by saying that the swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in the swampland. Therefore, fine-tuning, such as hierarchy problem, electroweak hierarchy, may end up having different solution than is expected from particle physics. There are severe restrictions on consistent quantum theories of gravity, and these ideas suggest restrictions on light matter fields. And positive energy in the concept of quantum gravity lead to local and global instabilities, may explain the coincidence problem via graviton excitations in a micron scale fifth dimension. And new ideas, namely dualities, are expected to play a key role in the very early universe. Thank you very much.
Okay, so if there is any question, I'm coming with the microphone to.
Don't be shy.
Sorry, I have a very naive question. So does the De Sitter conjecture imply that there cannot be a De Sitter landscape and therefore anthropic explanations of the CC problem do not work? Is this correct?
So it goes in that direction. So now the question is how, first of all, the De Sitter conjecture tells you that there are different versions of them. One of them is that in one version there is no metastable De Sitter. So that's already one answer. The other one says that metastable De Sitter may exist, but their lifetime is very short. So this would tell you that the idea of the idea that the anthropics was used to try to explain this was trying to solve the basically relate to coincidence problem. So these ideas tell you that that's not the right solution to the coincidence problem. The coincidence problem would have a different origin in this context. So what appears to be like remarkable, magical cancellation, equalities and so on, could have a natural explanation because the prior is different. So yes, this indeed casts a doubt on those explanations.
Thanks. And I can ask another question since I have the microphone. At some point you have shown that you can relate the bound on the cosmological constant to the lightest particle in the spectrum.
Yes.
Isn't this a solution to the CC?
Exactly. Thank you. I was going to say that. You see,
if you know the bound on the neutrino mass.
Very good observations here. Absolutely. So as he points out, I said that the mass, there's a relation between the mass and the power of the cosmological constant for the light states. That is, if lambda is small, there must be a light tower whose mass goes like lambda to some power. So let me just write it down here. Where A is some order 1 number. So he's pointing out that this means that lambda is mass to the power of 1 over A. And here I'm taking the case where lambda is going to 0, which of course means m goes to 0. But then this tells you that in this limit, the mass being small is determining the cosmological constant. The heavier states do not determine the cosmological constant. And that is precisely the cosmological constant problem. The cosmological constant problem is, why don't you get some heavy states, like UV cutoff, to the power of 4th contribution to the lambda? Why don't you have those? And in fact, why is it so small? The distance conjecture says it has to be like this. The light state is what dominates it. We have examples in string theory how this exactly works. And what we learn from those examples is that the states that are UV are composite objects compared to these guys. So they are made up of these guys, and you have already included their effect in this term. So it would be redundant. It's like in the quantum field theory, when you take the loops of particles, you include charged electric states, not magnetic states. Like magnetic monopole, we don't send in the loops in the Feynman diagrams. They're composites. Similarly here, it turns out that these objects end up being composites of these guys. And so indeed, this is a solution to the cosmological constant problem.
But here you always have supersymmetry? Or
no.
No.
No. So let me give you a simple example. Consider bosonic string theory. Has no symmetry, there's no fermions. In string theory, we discovered that even if you take bosonic string theory, with string coupling small, let's say G string goes to 0, string coupling goes to 0, you get a light tower of states. What is the light tower of states in the limit that string coupling goes to 0? Well, the string themselves are the light states, because in Planck units, the mass of the string is going to 0 with some power of G string. So indeed, in Planck units, m string over m Planck, is what is light in the limit as G string goes to 0. Okay, so you take the G string goes to 0 and you get a light particles like this, and you find that as G string literally goes to 0, in fact, if you equal it to 0, the only diagrams in string theory that contribute are spheres. This is the analog of the vacuum diagram of string theory with no loops. The loops would be torus and higher loops. If you compute the vacuum diagram, the contribution of the cosmological constant for the sphere diagram, this gives you some value, which is the value at genus 0 of this partition function, the free energy for that sphere, but you have to divide it by the volume of the symmetry group. The symmetry group on a sphere is the conformal group, which is SL2C, whose volume is infinite. So this indeed is 0. So indeed, even for bosonic string theory, the cosmological constant is 0 at free level. And that's the reason, even though it didn't have to be. And then you can say, okay, what about higher loops? You do the higher loops for the theories which have no tachyons, which are non-supersymmetric. And there are examples. For example, there are 10-dimensional theories which are not supersymmetric and have no tachyons. An example is SO16 times SO16 gauge theory in 10 dimensions. At 0 level, genus 0 level, the vacuum energy is 0. At one loop, they do get contribution to the vacuum energy, and their vacuum energy goes like m to the 10, where this is the string scale to the 10. And there is no term corresponding to the Planck scale to the 10, which you would have expected to be there. And you say, why isn't there? And in fact, when you trace it to the computation in string theory, you find that it has to do with the fact that when you're doing string diagram contributions, the computation that you end up doing is cut off compared to field theory. The field theory has extra region that you integrate, which gives you this term. And in string theory, it's cut off because of a symmetry, which is called SL2Z, which comes from the following simple symmetry. At one loop, this is a picture for a string, and there are two sides to which string goes. You can think about string going this way, or you can think about the string going the other way. If you convert the space to the time, that's a symmetry, which is absent for particle physics. Using this symmetry, you get rid of this contribution, and these terms are already included here. And this is small contribution, so exactly like this. So the cosmological constant problem is just solved by saying that the light modes dominate, and the heavier modes are composites in terms of these guys. And it's nothing to do with supersymmetry. Hey, there's a question up
there. Thank you. I am an experimentalist, so the amount of things I understood is probably of measure 0, but it doesn't matter. One point I got is that you are using the existence of Hawking radiation to make many of your proofs.
I can't hear you.
You are using Hawking radiation and in black holes as
Yes.
some of the element of your
Yes,
proofs.
yes.
Hawking radiation is something we don't know if it really exists. We never
Yes.
measured. It's a theoretical assumption that is obtained by assuming, I think, that you can use quantum field theory on the surface of the black hole. Is it not a circular argument? Because you are using something that then you deduce, or at least some consequence that might be within the hypothesis of the radiation itself.
It could be, you could view it that way, except I would say not really, because the argument that Hawking is using at the weak level, namely semi-classical gravity. Classical gravity, we believe, is true. That in some sense, in the regime of the large radius with low curvature should be true. And if you believe that should be true, semi-classical cannot be quite wrong. So there should be some validity, and that's what Hawking is using. So I think you have it's not avoidable.
Yeah, but charge conservation, for example, it's part of electrodynamics. So if you use electrodynamics on the surface of the black hole, you are in some sense assuming that charge conservation is not spoiled by gravity.
Charge conservation is not spoiled by gravity, that's correct. But global charge, not electric. So there are two different notions of charge here. Charge conservation, if it's gauged, if it's electric charge, it's not spoiled. But if it's not electric, then it is spoiled because of gravity, because of the gravity. So, in fact, both of them Hawking himself calculated. So he computed, for example, the proton decay because using gravity, using the black holes. So in other words, the semi-classical argument of gravity should be true. That's because we don't have a strong region, and the computation that Hawking did was around the horizon, which could be very weak gravity fields. So therefore, it's reasonable to believe it's correct. Now, that was done without any regard for string theory. Long before string theory was really shaped up. But the very fact that we get the same things from string theory independently reinforces Hawking's idea as well. So these things reinforce each other. But it's a totally different idea. It is not because of strings or some crazy features of an extra dimensional object. So it's different modalities, they lead to the same thing. So they reinforce each other. But I would say that Hawking's idea is more basic than the string, what we see in string theory. So I would present that as the more fundamental reason.
Yeah, more naive question as well, experimentalist here. What can we do to search for the magnetic monopoles, if they must be there?
What do we do?
Yes, what can we do? Like you said that they must be there if string theory is true, right?
Well, first of all, I should ask you. You said you're experimentalist.
Yeah, well,
That's your homework.
not
Go and
like,
find
yeah. Not in string theory, let's say.
No, but I mean, I'm not saying things are easy to measure, but I mean, people have tried to measure the magnetic monopole and so forth, but we don't know, first of all, what their mass is and so forth exactly. Actually, we do have a prediction, I should say, about their mass. Their mass cannot be much more than 10 times the Planck mass. How do I know that? Weak gravity conjecture applied to magnetic charge. So you learn an upper bound for the mass of the magnetic monopole, nothing to do with grand unification or anything like that. So we have an upper bound for the magnetic monopole mass. Yeah, it would be interesting to do the experiment. Some people have tried to search for these guys, but it's not easy. So I mean, that's one good question. The other thing is that, but you could ask, are there any of these things that I told you about that can be checked? So indeed, people are trying to check it. In fact, I'm happy to tell you that experimentalists are now trying to push the bounds on the violation of 1 over r, by deviation from the Newton's gravitational 1 over r squared law, to see if that distance scale can be less than or order of the micron. In other words, if we are making a prediction that there's a 5th dimension of the scale of a micron, then you expect that, so you think about this as an extra dimension, if the distance scale between the particles is much bigger than the micron scale, you still expect the 1 over r squared force law to hold. But if the distances are much smaller than the extra dimension, then the modes of graviton in the extra dimension come to play. And so 1 over r squared force law becomes 1 over r cubed force law. So the 1 over r squared becomes much stronger at shorter distances. This could be measured if you measure the distances smaller than the scale of this extra 5th dimension. So the theory is effectively 5-dimensional. So up to now, up to 30 micron has been checked that Newton's law holds. So if you go up to 30 microns. So we are making a prediction that if you go a little bit lower down, not too far down, you will see a deviation from 1 over r squared. This is striking. And indeed, there's Adelberger and his group have already done the experiment which give you 30 micron as the bound. That same group, with also the Viennese the colleagues in Vienna, are trying to extend this to 10 micron regime. So trying to make it smaller. We want even smaller because we don't know the exact size of the extra dimension, but it's of that scale. So it's they can potentially see it even in the 10 micron, we don't know exactly. But we estimate the range is around 0.1 to 10 micron for the extra scale. So those are experimental potential observations. So these are really not only observational, it's a bit scary because they could be ruling out the various things I was telling you. So we are very close to experiments now.
Thanks.
You want a question? You want a question?
Yeah, so to connect to the previous question by Marco Pallavicini, so semi-classical Hawkins computation also predicts some contradictory features, right? Predicts that unitarity is broken, okay? So how much of these semi-classical gravity predictions should I believe and how much should I throw
Well,
out?
these are questions, I mean, I wouldn't say it's contradictory. It's just, it raises a puzzle that we're still struggling with understanding, the information puzzle of unitarity. The very fact that features of this has been reconfirmed in string theory, I think validates, in some sense, strengthens our belief that they're both correct. We just have to understand how. So features like entropy has now been validated completely independently and gives you the same answer Hawking was predicting with very different ways of thinking. So we believe various features are correct. Now, the issue of the black hole information, we still haven't resolved, and we're still debating among string theorists what's the resolution, and we still don't have a good concrete answer. But it doesn't mean that we don't trust any aspects of black hole either. So the many features of the black hole physics are, we know, pertinent, and a lot of these conditions I just told you just directly follows from some basic aspects of black hole. So I think that the fact that these aspects are consistent with string theories reinforces the view. But they were independent derivations, I would say, nevertheless.
Sorry, I can't avoid the question. Since you mentioned the Higgs naturalness, what's your take on that? In light of
Higgs what?
Higgs naturalness. Higgs
Yes.
the problem. You also mentioned it.
Yes.
In light of the discussion about the CC, what's your take?
Yes, actually, I didn't tell you the whole story with the dark dimension. So in a series of couple papers we wrote, we connected the hierarchies, all of them, to the powers of lambda. So there's only one hierarchy, which is the cosmological hierarchy. So in this context, we find that so we have the lambda, which is the dark energy. We find the mass of the neutrino is 1/4 power. We find the Higgs scale, Higgs wave or Higgs scale, is of the order of the 1/6 power. We find that the lifetime of the universe is of the order of the -1/2 power. We find, or the age of the universe can be of this order at most. We find that the higher dimensional Planck scale, the fundamental one, is the 1/12 power. What else? So all I'm trying to say is that everything is coming with some powers of lambda. And this is precisely what is expected, what would be an explanation. That is, there's only one scale in your theory, and everything is pegged to the power of that scale. This is related to Dirac's large number puzzle. Why are these things that we see in physics are related by powers of each other in some form? This is explaining it. That is, they're all related to one object with some constant, but it's always raised to power. Why is it raised to the power? Because of the distance conjecture, which is exponential. So the exponential to some constant means exactly these powers, appears as powers of lambda. So therefore, this is beginning to be precisely what we expect, and seems to match with our universe. And the existence of two different scales in particle physics, neutrino, which is much lighter, and the Higgs scale or weak scale, which are very separated, and then the Planck-like scale, and the age of the universe, and so forth, which are yet another thing. These are all now coming together in terms of one object. So then the issue of the fine-tuning or electroweak hierarchy and all that is just related to one question. Why is the dark energy so small? If you say whatever value you choose, you can predict what the rest of the values are for the would-be cosmology or the particle physics based on that one parameter. And why that's small is the only rationale that I can see for that as of now is that the entropy is also related to the inverse power of lambda. So the why the lambda should be small is because we want to have a big entropy. So in a universe which has information and something, you need lambda to be small, otherwise there's not much information. So therefore that is quote unquote anthropic in the sense that just you need information, you need entropy. But that's the bare bones of the anthropics that we're going to use here. There's a question up there.
one of the discussion you had, there was a breaking of supersymmetry. I had a question more general related to that. So we know that supersymmetry is broken in nature, and so I was wondering how much of these arguments then, how much can we save of these arguments if supersymmetry is broken to, say, a given scale or something?
Yes, so I did not use supersymmetry in these arguments. In fact, the question was asked here about the dark energy, and I explained very specifically that the cosmological solution to cosmological constant problem is nothing to do with the supersymmetry. So we are not using supersymmetry at all. It is true that most of the detailed examples we understand is supersymmetric, but we also do understand some features of non-supersymmetric ones in certain regimes of parameter, like weak coupling, strong coupling, weak coupling of strings, and this and that. And they fit with the same pattern. It doesn't change the story. So therefore, we don't think supersymmetry runs the show at all. It's just that we have more examples that we can trust in that way. For example, the black hole arguments have nothing to do with supersymmetry. And they work, and it's consistent with what we see in string theory. So in other words, partly it's that it gets mistaken to think that supersymmetry is an important ingredient in theoretical existence of string theory, because that's how it came about. Now, one feature is true. Supersymmetric solutions are the only ones which are stable. That's true. So supersymmetry plays that key role. If you want a universe which is stable, you need supersymmetry. Anytime you break supersymmetry, that universe is doomed to decay. It's not going to stay forever. Supersymmetry in that sense is fundamental. But, you know, as metastable, as unstable states, like our universe, we could exist.
Maybe we can call it off, and thanks, Professor
Thank you,
Vafa,
everybody.
for this interesting lecture. I thought it was enough.
Lo vedi che sono vecchio stando, posso? Quella è l'unica cosa, diciamo, solo la banca. Max no, quella purtroppo non è sua. Purtroppo non è sua. Infatti dicevo, analisi. Quella è incredibile, quella parte lì con la graffa, perché dice che praticamente un sacco di cose diverse, tipo la terza è l'età dell'universo, sono multipli di lambda, che è una costante che riguarda cosmologica, che c'hanno multipli potenze di lambda. Quindi tipo l'età dell'universo, il tasso di espansione dell'universo, la massa penso del neutrino, sono tutti legati da questa costante. Sì, che non ha senso, è incredibile. G è Gauge. G non sarà qualche tensore assurdo. Secondo me tutti quelli lì con i pedici sono tensori. alla quarta e LUV alla decima. SU penso sia un tipo di teoria. 2. Ne ho detto una, poi ho detto una sigla di una teoria, ho detto questo per esempio si presenta il volume di G, chissà che sarà. Pazzesco. Quello era un volume, giusto? E dico la sfera. Secondo me non è un volume nel senso comune del termine. Che è uguale a infinito. Stai guardando su mi sarà qualcuno che tanta grande per io. Lui ha detto LU. Sì, ma come facciamo? Lo dividiamo? È quella roba lì.
Questo è il pane.
Però non è finito, vediamo è quello lì a sinistra secondo me.
Non è quello lì al centro?
Io pensavo fosse a sinistra. Era qua è tipo la vera croce di tutto che ci sono le teorie. No, sì, ma qual è il vero? Magari ne ho usato più di uno.
Se no Fra, ho un'idea. Andiamo, lo seguiamo, prendiamo un capello e prendiamo dei gessetti, facciamo un'analisi del DNA.
Oppure gli chiediamo qual è stato gestito cosa. Quello è il suo modello.
Beh, di sicuro l'ha usato quello comunque ha usato la cosa che ha scritto.
Sì, ma
Te lo sniffi.
potremmo raccogliere la polvere. Capisci che possiamo dire di aver scritto la stessa lavagna, l'ha scritto lui.
Prima di lui, tra l'altro.
Prima di lui.
Vengo prima di lui.
Pazzesco.
Addirittura qualche infinito ce l'avevo pure scritto io.
Infinito. Il volume è
Ho scritto pure le stesse cose.
Perché è un volume di una sfera, tra parentesi. Quella cosa lì, quando ha fatto quel cilindro, quel coso che scende ma è tagliato. E poi ha detto quello lì è
Spazi organizzati peggio di Baronti.
Alla decima è quel pezzo. È partito da lì e ha fatto una sorta di spirale, è andato giù e tornato su e è andato là. Sì, poi lì ha cancellato. C'è un layer sottostante.
Madonna.
Ha lasciato le slide però.
Adesso ti facciamo la pennetta, aspettiamo.
La pennetta di Harvard. Ma è tipo Swampland. C'è la pennetta di Harvard. Sono tutte, sono tutte le teorie quantistiche dei campi iraniane. Tutte le teorie quantistiche dei campi che non accettano però la gravità.
Quindi già capire in italiano.
Non sono compatibili. Cioè devi pensare che ci sono tutte queste teorie infinite che sono legit, teorie quantistiche dei campi, ma solo un numero finito è compatibile con la gravità. No, che immaginate ad esempio di avere una teoria le parole in grado di
Sono stati per il discorso.
immaginati ora facciamo un discorso che non ha senso, la gravità, la forza gravitazionale, la teoria gravitazionale universale gravitazionale di Newton, se G fosse libera, cioè invece che avere un valore fisso, noi potremmo dire G vale il doppio del controllo. A seconda di ogni valore che ci dai è una teoria diversa. E quindi hai un grado di libertà, a seconda del valore che dai G. Se avessi due parametri liberi avresti due gradi di libertà. Lì ci sono infinite possibili teorie, perché ci saranno top gradi di libertà, ma quando tu poni come condizione che sia compatibile con la gravità, diventa un numero finito. E quindi loro dicono, come le troviamo queste? Non abbiamo visto mai in nostra vita una teoria che abbia almeno un grado di libertà? Non lo so. Per capire il concetto. Non lo so. Tipo, abbiamo un esempio che conosciamo. Cioè, tipo, non so se abbia senso dire la forza gravitazionale, se consideri G come grado di libertà, praticamente, forse per me più giù. Se metti G che è più grande,
I gradi di libertà che sarà più?
ma perché noi siamo
il
in
numero
un
di
universo.
punti meno.
No, G non credo sia la costante di gravità. Cioè, tipo se noi fossimo in un altro universo, avremmo un'altra teoria. Cioè, ovviamente nel nostro universo poi ne vale una. Non possiamo avere due cose che valgono tra. Penso che sia questo. E loro dicono che per trovare quella che comprende tutto, invece che cercarla, escludiamo le altre, perché è più facile. Cioè, invece che cercare la teoria del tutto, escludiamo quelle che non vanno bene. Quindi guardiamo quali criteri non deve soddisfare una teoria, cioè deve non soddisfare una teoria per rientrare nel complementare di quello che diciamo bene, cioè nello swampland. 23 sono quelle buone, penso. 23 teorie sono? Quelle devono essere almeno 23, con 4 dimensioni. Non ne aveva 10 dimensioni? No, 10 è la teoria, 4 non sono vere. E tipo la nostra, quella che adesso stiamo studiando è il modello standard, che è quella con tutte le particelle, 12 particelle, i 6 quark. No, che noi adesso usiamo. È quello sì, ma l'hai visto sicuramente, il modello standard. Dunque i quark, gli elettroni, i neutroni, penso sia quello perché compariva.
Diciamo dello standard, perché le particelle sono quelle buone, poi c'è la palude fuori.
Se mi piacciono i diagrammi così, che sembrava proprio prova diceva il puntino che diventa una stringa. Poi 10 secondi dopo c'erano i manifold.
non buone, in quelle buone, cioè quella...
Il bello standard.
Il bello standard, e poi sono le altre che sono veramente buone.
Comunque secondo me siamo in live. Sì, siamo in live quasi sicuro. Mi è arrivata una notifica ieri che c'era live.
Sì?
Sì, infatti, eccolo. Eccoci.
Accendiamo il microfono.
Se ricordate di mettere.
No, allora godo perché così giovedì che non ci sono, posso prendermi l'altra.
Possiamo anche riguardarci. Guarda, c'è un'altra. Però in ritardo, eccoci, sto girando. Siamo ancora
Perché se ne stanno andando.
Salutiamo. In ritardo. Vabbè, quindi io niente, non prendo la stessa.
Non prendiamo il tempo.
No, siamo in videochiamata.
scritto la lavagna che cosa... che cosa? Ah no, mi sa di no perché è in italiano, quindi non è sicuro lui.
Questa roba mi sembra molto analisi 1. Tipo le cose più facili di analisi 1.
Sì.
Tipo il teorema di Rolle, la grande.
Sì, mi sembra potrebbe essere anche tipo il teorema degli zeri.
Hanno una bella resistenza questi gessi.
Sì. Guarda che brutta che la lavagna.
No?
No, è orrenda, una ansia di uomo.